Let's take a look at how supply and demand of energy are matched. We'll focus on electricity because most renewable energy becomes available as electricity. Traditionally, electricity is generated in power stations like hydropower stations, coal plants, nuclear plants, gas plants, etc. But increasingly, it's generated from renewables such as solar, wind, and biomass. On the other side, there are different groups of consumers, such as commercial users, households, as well as emerging demands like electric vehicles and increasingly battery storage with the grid in between. We'll focus on how supply and demand are balanced, not on the infrastructure itself. The primary challenge is that the demand for electricity changes all the time. Electricity demand constantly changes, and supply must match it instantly since the grid stores no energy. Now, in markets with a lot of rooftop solar energy, the observed demand goes down when the sun shines as the solar energy offsets consumption. When we observe the demand pattern for a month, we can see the weekends are marked by lower demand, and over the course of the year, the patterns are very climate dependent. So let's see how supply and demand can be matched at any moment. In an efficient electricity system, we start with the cheapest energy source first. Typically, solar and wind come first, followed by other sources like nuclear and gas-fired power plants. We select them based on operating cost. Given the set of power stations, we want to minimize the cost of electricity production. In Europe, there's a price for CO2 emissions, so the operating cost typically consists of the fuel price plus the CO2 cost. Now, when the demand increases, more expensive resources are needed to meet it, represented on the x-axis. We call this the merit order. The merit order of supply means that power plants are sorted based on their economic merit, namely their operating costs. As demand increases, the market price rises because more costly plants are needed and they want to cover at least their running costs. Now, when we transition to renewables, the system gets a bit more complicated. Here we see the picture of 6 days with a demand and a certain amount of wind generation in blue and solar generation in yellow. With more renewables, supply fluctuates. Sometimes there's a surplus, sometimes a shortage, such as during calm winter periods. The gray area is the demand that's not met with renewables. The remaining demand is covered by fossil or nuclear plants and sometimes hydropower. Hydropower provides flexibility but is limited worldwide, so other flexible options like shifting demand and storage are needed. For example, electric vehicles can charge when renewable power is abundant, and heat pumps can shift their operation to low demand hours. And finally, we have energy storage. With battery storage being a rapidly growing industry, its idea is similar to demand shifting, but a little bit more straightforward. Battery storage absorbs surplus solar or wind and releases it later, covering short-term gaps between supply and demand. However, they're less suitable for long-duration storage. For instance, in my country, the Netherlands, we can have multiple weeks in winter where there's not much wind and limited solar available. Batteries don't have the capacity to cover such extended periods, at least not with the current technology. For longer storages, we may therefore need energy carriers like hydrogen or ammonia. Next time, we'll look at how the market helps to optimize supply and demand. Thank you for your attention.